So that's a little.
In fact, you can do a minus one or plus one even, right? That also works, right? But it's amazing that something this simple should work. Yeah, but as I don't know what happens as L gets close to N. I'm not totally sure, but that could be the problem.
Yeah.
Okay.
Thanks.
All right. So let's get started. So welcome back. So today we're talking about noise in data. I'll touch on another use case of the SVD inside the lecture as well. Before we start, there is going to be a meeting of the Data Science Club pretty much 10 minutes after this lecture. I guess it's going to be upstairs. And it'll be some tutorial on doing some basic deep learning in Keras. So if you're interested in doing that, you're welcome to join them. If you're not getting on a mailing list for this, you can go to datascience.utah.edu and go to the club link, and you can find out more and pay attention to this. I don't know. Maybe this is the last one of the semester. Oh, there might be one more this semester. Cool. So if you want to get advance notice of these as opposed to 90 minutes before it starts, then you can go and get on the mailing list. And then there'll be more cool stuff probably in the fall. Okay, great. And then also, so the projects were due today. So, no, yeah, okay. April Fools, yeah, okay. That was, okay, that's probably the best I've done in last 10 years on that front. So, okay, so there's the projects that's due for a while, not till April 15th. So the dimensionality reduction homework is due on Wednesday, and so I posted on Canvas. Where's this one? But there's a there's one change I had to make. The scaling on for doing the Johnson-Lindstrauss. You can take on just a normal random variable inside of here. It can be all independent, but it should not be square root n over L. It should be square root L over n instead. If you put S on the other side and you're doing dimensionality reduction kind of from the number of columns being compressed, it basically it's the other way, but in this direction, I've gotten these flipped. So it won't converge if you use that one because you're going to be scaling up too large. All right. So just make sure you see that. Was there anyone who turned it in before that announcement? I don't think so. So it should be okay. Okay, good. Right, and the other stuff you have to write. A couple people talked to me about. There's a little piece of MATLAB or Octave code I ask you to write here. I give you a stub file. Shouldn't be too hard. Some people try to do it in Python. You can definitely do it in Python. You can get to work. Python is a little bit trickier to do it in, just because of some weirdness sometimes in how it does linear algebra. But that should be possible. That'd be fine too. If
one of the things that I had the challenge with doing Python is when you do the slicing of the matrix. MATLAB is index 1 based, so from 1 to whatever it takes the first element. Python is 0 based, so you have to account for that.
Yep. So there's a number of small changes. The default SVD does not give you back 3 matrices that you can multiply back together again. So there are kind of a few different things you have to worry about. And sometimes Python does stuff a little bit weird in this space as well, but it should be possible. Or any other language, C, Java, R even, you can do it. That's fine. Okay. All right. So we're talking about noise in the noise and data. And so hopefully by this point in the semester you realize that like just about every data set you have will have some sort of noise in it. It's not going to be, it's like the data set's not going to be perfect. It's not going to, the data's not going to exactly fit the model that you're trying to have. There are probably most of the other courses you take as part of your degree, unless you're in a stats program, are going to be dealing with data that you might not assume has noise in it, right? So hopefully, if you have an algorithms project, you might not assume any noise about the data, right? If you're even maybe a scientific computing class, you might assume there's not noise. You want to get down, given what the data has told you, down to something like 10 digits of precision, right, in some sort of calculation, because you believe the data you have tells you that much precision. Maybe beyond that, there's other sorts of noise, but that's not what's going on here. There's going to be lots of noise in the data. And so kind of just to start off, and we'll come back to this, is that we'll typically assume that there's some sort of model, and this is trying to fit. There's some data which is close to this model, right? And so if the data were to lie exactly on the model, you would say that's when there's not noise, because the model is exactly trying to fit this data. And that's the opposite of what we're thinking. In this class, it's not going to be exactly on there, and that's kind of what we're mainly dealing with in here. This model could be a low-rank subspace. It could be a linear function or a polynomial function you're feeding to the data. It could be the centers of clusters. It could be lots of other kind of sorts of things. But I think generally that this is what you think of as the model, and the data does not lie exactly on the model. I wanted to start by just trying to kind of try to categorize the different sorts of noise you would tend to see in the data. So the first type would be where there's like spurious readings in the data. So these would be, you would think of these like, these could be like, if you think of noise as being outliers, this would be outliers, for instance. If you have a data point way up here, it's not close to the model, right? So is this part of the model? Should I be trying to fit the model to this piece of data or not? These are kind of the questions with this sort of data. And this could arise because this data might be being collected by hand. Someone can send out surveys and they're going to miswrite. They add an extra 0 onto something, right? This happens, right? In automated ways of collecting data, there are other sorts of errors. There could be some bug in the code, or there's kind of some weird interaction with the automated system, and you get something that's totally out of the range of data, right? So this would be one type of noise. There's another common one, which I'll call like the measurement error. And that's more what you see here, right? This is kind of fairly simple, right? From every data point, there's some error that is occurring. And this could be because there's actually a simple model that's going on here, but when you've collected it, maybe you've rounded the data in some way, or just you're using kind of like some sort of sensor, like you're using a picture or video to try and gauge the depth to an obstacle, and you're trying to do like stereo computation from 2 images, and it's not exact because it doesn't perfectly align stuff up, so you get a little bit error in what the depth of a data point is, right? Or you're just measuring something and it's you don't quite get the right reading here, and so kind of it's useful to often assume that this data is is going to be Gaussian, right? There's a few reasons so for this. One is it's a very simple model. Two, kind of when scientists observe noise and data in various places, it often looks Gaussian. When you have lots of readings coming from independent processes and you average them by the central limit theorem, it will eventually converge to a Gaussian in some way. So Gaussian does not need to be, if you think of this as a high-dimensional Gaussian data with Gaussian noise, this might have some variance that's different in the different coordinates, or it might have this covariance where two things vary in the same way. You can capture this with a Gaussian. Also, this Gaussian kind of, there's a way, if you write down what's essentially the log likelihood or the negative log likelihood, and you minimize, it's called the negative log likelihood of data coming from a Gaussian, then this is going to turn into the sum of squares error, which, as we know, looks like this L2 norm, which is Euclidean distance, which is just showing up everywhere, right? So if you assume Gaussian noise, then you can often use Euclidean distance or these typical norm calculations that we're using in here. And so I didn't do too much example derivatives of like how you can get from these to the other in this class, but if you look in the book, there are several examples of this. So it's kind of a pretty nice thing to kind of assume here, if not in kind of formally, just intuitively, that there's some kind of Gaussian noise coming off of here. So here, the lengths of these green lines might look like they're Gaussian. Or if I looked at any one projecting onto any one direction, they could also look Gaussian. That's another nice thing about the Gaussian, is that it's symmetric under, it's still Gaussian if you project it. Right, so this is kind of an intuitive thing to think about here. This sort of data definitely occurs. And then a third type might be some background data. And this is kind of different than these other types in that this might be data that you don't necessarily want to fit onto the model. It could be that I want to fit this curve through the black points here, maybe minus the outliers, but that there might be this other kind of noise there's some other data in the background here, where there's just some other data points generated from a different process than being close to this line. This doesn't often come up like in regression, but maybe if you're trying to kind of cluster populations of people like in the U.S. or in Utah, there are going to be these people who live out on these kind of these farms, and they're not really part of these population clusters, but they exist in the background, right? It doesn't mean you don't want to cluster them, but if you're trying to fit distributions around cities, then these are from some different distribution of people, right? This can occur in other sorts of scenarios as well. So this means there'd be background data. I would also throw into here, you could have some issues with missing data. So this is kind of be like other background issues going on. You're trying to find a low-rank, low-dimensional model for data, but for a lot of the attributes might be missing. Okay, so in this lecture, I'm going to actually talk about how to deal with some missing data in the context of the SVD. Actually, if you go back to here, I updated the notes for the noise and data right before class, and I added a section on it's like missing data as a matrix completion problem, right? So if you hadn't noticed, I just did it this afternoon, so that's something else to check out. So this could be missing data. You don't have measurements everywhere. How do you deal with this when trying to fit data? Okay, so I would say these are probably the three most kind of common categories of ways to fit data, and you deal with them in ways which are kind of usually like like fundamentally different. Okay? The Gaussian sum of squared errors, basically by fitting the best model to something, minimizing like sum of squared errors, you're probably going to do pretty well. That's just this kind of a natural sort of like harmless noise. This background data, or if there's missing data, you need to use maybe special techniques to fill this in or to kind of try and factor this out. And the outliers, we'll talk about these as well. For the outliers, there's nothing especially tricky, but there's some kind of conceptual ideas, and there are a couple of techniques I'll describe to help you kind of circumvent these conceptual sort of ideas. So we'll kind of talk about those. I want to add one more category that when I first kind of made the notes for this class like 5 years ago, 5 or so plus years ago, was not really on anyone's radar. I mean, maybe some like people who work in algorithms and theory, which should have been someone like me, but there's this new sort of adversarial. I'm spelling that wrong. Okay, so someone help me out here.
S-E-R-I-A-L.
S-E-I-A-L. Gosh. Okay, this is why I should prepare my notes better so I can. Gosh. Okay. Adversarial.
There you go.
So data. So this is sort of data where, you know, it could be something in this form, but it's not something that's caused by like a process where there's like okay, there was sensing error or there was an accident. This is where someone does this on purpose. Okay, someone's specifically trying to be kind of make your life as difficult as possible. Okay, so, and you know, not necessarily a professor in one of your classes. Hopefully that's not what they're doing. But someone who's trying to make your mining, your data mining, your learning kind of process, kind of they're trying to challenge you on this. And this is kind of like there's like an algorithm's perspective. I can guarantee I recover this in the worst case, no matter what anyone did. And so people had studied it in that ways, but not necessarily in the ways these had like imagined. So there's been some cool things in that people have studied these models like in deep learning, okay, which are these, what they end up being is these, instead of these more understandable, intuitive models we've talked about in this class, they become much more complex models that we have a hard time understanding what's going on. They tend to work super well in practice, as you've probably all heard, or you can find out in the tutorial after this lecture. But what can happen is that because we don't totally understand why they're working, or maybe we do understand why they're working, people have shown that you can add in certain data to your training set that will make the model learn something which isn't what you intend. So an example of this is people have trained classifiers to classify whether an image is like a panda or not, and they've added in a bunch of data that looks like pandas, where say the very bottom left pixel is going to be all white. Okay, and so most images do not have it all white. But it turns out if it's a panda, they made sure everything in the data set had this pixel all white. And so then anytime it saw any other image that had the pixel all white, it said, okay, it's probably a panda because this was directly correlated with everything, all the other pandas had this property, right? And you wouldn't notice this, right? So this would be an example of a single like outlier coordinate, which could fool all the things into predicting something's a panda. You can also do it with this kind of measurement noise where they added a very subtle but small amount of random noise to all the pictures of pandas. so the images don't look noticeably different. But it's because that signal, which ends up being a very small vector in high-dimensional space, separates the pandas all off in this weird direction. And so again, you can separate them. So you add that to other images, and it will also kind of say, oh, it has this vector in this direction, and it will pull them out. Okay, so these little things that you can add this adversarial data to try and trick what's going on here. So this is new on kind of the bad side, and that's fixed things. What's exciting is that in the last probably only 3 years, is there's been a lot of progress in how to deal with this more effectively. So I've mentioned it, I think, in the regression lecture about these robust estimators, where you could, the median is much more robust than the mean in one dimension, because you can have a bunch of outliers and the median is not going to move too much. In higher dimensions, this is trickier to do. How do you define the median the right way? And it's not as clear. And it turns out maybe in this median analogy is what we've realized in the last 3 years especially is that this median analogy is not quite the right way to think about it. And the mean is the right thing to do, but you somehow need to filter out outliers, and not just outliers, but data that looks like the measurement error. So it looks like it fits the distribution, but someone's put it in there in a way that was kind of coordinated across them, right? So this panda example where I added in this fixed noise vector to everything, I want to detect that there's this weird fixed noise vector and factor this out. And there have been a number of settings where people have figured out how to deal with adversarial data like this with guarantees that if there's only 10% of this adversarial data, I can recover from it. Okay, these have worked for things like linear regression and predicting a single mean and maybe things like k-means clustering, but they're not quite to the level that they understand this for deep nets and stuff like that yet. But so there's been some cool kind of work in this space recently. It's still in the early phases, but that's been kind of a cool kind of a fairly cool development. Okay, so we're mainly going to be talking about stuff that is where people do not intentionally try and make your life difficult, and how to recover from those situations. And that's actually the first line of defense here as well. But then there are situations that kind of slip through the cracks beyond that, which I'm not going to cover in this lecture. Maybe ask me offline, and I can give you a little bit more hints into how this works. Although I don't have it in my head yet to distill it down into kind of how to give it in this lecture. But maybe that's something over the next few years I expect to be kind of some cool research to come out of. So great. So okay. Any general questions about what is noise in data? Something I've missed before we talk about a few kind of general techniques to deal with these issues. Great. So okay. So our first kind of our first technique, kind of to help deal with noise, we've kind of spent half of the lecture on already, so cross-validation and regularization. And so I'm not going to spend a lot of time on this here, but just to remind you what's going on here is you often have a model M of some data, which is going to be some arg min M of some sort of function that often looks like the model of the data minus the data squared, this least squares term, plus some regularization term here as well. Okay? So if you remember, this is kind of what least squares regression with ridge regression look like, and with ridge regression, I put the L2 here, or I can put, if I put a 1 here, then this looks like the lasso, right? This gave us a thing that induced sparsity as well. Okay, so by adding this regularization term, I'm biasing towards what ends up being a simpler model, right? So this biases towards these simpler models, okay? And models which are simpler tend to generalize better. Okay? They tend to do better on new data if they're simpler. Kind of one way to think of it, if you've seen like a Bayesian perspective on statistics before, you can think of this object over here, this as being like a prior. Okay, so I have a prior in what the model should look like. I want it to be simple. The prior says that I have very simple models. And then I have, you know, and here I have some observed data, which is also informing what decision I'm making here. And so as I get more and more observed data, I need to rely less and less on the prior. Right? If I don't have a lot of data, I probably want to rely more on the prior. Right? And so this is essentially what's going on here. And so one cool thing that's happened the last 5 or 10 years is we've got lots and lots more data, and regularization has kind of become a little bit less important. This is kind of why we're able to learn these really complex models, like in deep learning and other stuff like this. Even like random forest, these other complex models do much better now if you have lots and lots of data, because you can rely less on this prior for kind of keeping things which are simple, right? And so in order to learn this, you need to somehow set this term here, this regularization, so parameter, right? And I need to set this. This tells me how much weight to put on the prior versus on the actual data. And how do I know how to do it? Well, I can say maybe there's one way to say the prior is worth like 100 data points, and then you can just weight them that way, and that might be kind of reasonable. The other way to do it is I choose S with cross-validation, right? And so that means if you remember, I take X and I break this into 2 parts basically at random. Here, where I have the black would be the testing data, and the pink would be the training data, and I might build a model with the training data and evaluate on the testing data the value of S, which does the best in, like, which actually has the smallest residual in predicting on the testing data. And because if I assume my data comes from my IID from some unknown distribution, then this is equivalent to effectively like drawing new data I haven't seen before. Right, so I split these out randomly, and if I have enough data, I have enough trained data to still train these models which are reliable, and then I still have enough left over to evaluate how well I'm doing. Right, and so with lots and lots and lots of data, you can train very, very complex models, which maybe means this regularization parameter is small. Maybe it means I can look over large polynomials in what I'm building a regression with a very large polynomial. Those are things you can do with more and more data. So one other thing this is useful to point out, I mentioned this before, is that you may want to hold out some other data to test. So generalization, can you even read that? Nope. Okay. Okay. So generalization, I have this other data which is in here, which I also hold out separate from the training and the testing data. These are separate pieces of data, and I can kind of predict how well it's going to work on the future. Okay, so even the best models, if I have IID data, there's probably noise in it, and I'm not going to have zero error on that, most likely. And by holding out data and then evaluating how well it works on this generalization held out data, I can predict how much noise I get in my future predictions. Okay, so just keep in mind that those are three separate things. I want to mention one other tool, which is kind of a tool that somehow came out of the advent of computers, but also is useful for when you don't have so too much data, is the idea of so bootstrapping. And so this is where I'm, it's like cross-validation, that I'm pulling out samples from my data set, and it's like generalization, I'm using it to estimate how much error I'm going to have based on my model. But I want to say, given that I have, say, 100 data points, how much accuracy do I have in these data points? How good should I trust my prediction? And the idea is to for I equal 1 to, say, k, I'm going to draw n points. I'll call this xi from x. So with replacement. Okay, and then I'm going to measure model on the set m of x1, m of x2, up to m of xk. Okay, so what I'm doing here is I'm drawing out the same number of data points as I have into a subset, but some of them occur twice. So it's with replacement. So I draw some data points twice, but I end up, each of these are going to be the same size as the original data set. Okay, so this is called bootstrapping, and then I can create models for each of them, and I can say how much variance is there in each of these models, say using holdout data with generalization or something else, like doing leave one out regularization on these, and I can say how much, given the data I have, how much should I trust various parts of the data. So this is useful for looking at the models, which coordinates, kind of what term in the, let's say I'm doing a sparse regularization over some high dimensional model. And there are certain coefficients that show up and other ones which are dropped because their coefficients are 0, right? So which ones show up over and over again, even when I subsample the data, those are probably truly important, where the ones that sometimes show up and have a high coefficient but sometimes don't show up are probably not important, right? And this is not on a subset of your data, it's kind of these with replacement subsets, so it's kind of a representation of your true data here. Yeah.
Is there any particular way that you sample the data?
So each data point, I'm going to draw n data points. So I start with n data points, and I'm going to create a k different kind of representatives of the data set. Each of them will be of size n. Each point is drawn independently. With the same distribution, yeah. So it's assuming that, I don't know which, I assume that all the data points are kind of equally important in the eyes of this analysis, but some of them might be outliers, right? So maybe sometimes, if I happen to select that outlier, my model is going to reflect it and will kind of try and fit to the outlier. And when I don't, it's not going to show up, right? And so I might get this kind of, I might be able to kind of essentially cluster the models and see, okay, there are really two modes in the space of the models, depending on whether I selected an outlier or not. And this is one way of saying, okay, now look at one of those modes. That one happened to always have an outlier. Maybe that's where I can throw an outlier. That's one way you could use it. You can also look at the model parameters, as I was discussing, or you can look at the variance of the prediction. based on these. And it's used for a variety of these ways of kind of doing some sort of meta-analysis on your learning process without suffering kind of, I'm losing 10% of my data or 30% of my data for pulling out the testing of the generalization effect. Okay, and it's kind of in this family, and I just kind of want to mention it. So it's a cool tool to use. Yeah.
So when you do bootstrapping like that, does it ever make sense to add in some randomness into observations?
You could do something like that, and that can make sense. I wouldn't call that bootstrapping. That'd be something else. So something people do in learning to try and learn more robust models. I hadn't planned on talking about this appropriate. Is they'll take their training data and they'll create copies of it with noise. With some noise, they think this should be an acceptable type of measurement noise I might have observed. So I'll instead of having, let's say I have 1,000 data points, I'm going to take each of my data points and create 5 copies of it, and to each add a small amount of measurement noise, and then train on that 5,000 dimensional or 6,000 kind of data points instead. And this tends to be actually more robust. You can show that doing this tends to generalize better in certain, if you're adding the measurement noise in the right way. Makes it slower because you have more data points, but it's, if you do this in the right way, this actually improves how well your learning or your fitting of the models works. But bootstrapping would be assessing the actual data that you have and the models you build with respect to that. Right? It's more of kind of, I assume that I've got this well-manicured data, and I have a very good sense, and I'm trying to assess the sort of models I'm learning, how good can they do on the data that I have. So think there's this kind of study I know some people here work with. They've been collecting these like brain scans of people who've, but people who they've come back at 2 sufficiently separated times and gotten different scans of their brain. And there aren't too many of these instances out there, and each time you do this, it's pretty expensive to collect the data. So they have these like several hundred data points, which is not a huge amount, but they want to learn very complex things about how the brain is changing. And so it's a very kind of specific data set that they only have so many data points, and they want to know specifically what can we say about this. They can't just go out and easily get a lot more. Each time they essentially get a data point, it costs thousands of dollars. Right? So that you have to be very careful. What can we say about precisely the data set that we have? Right? And tools like this are important then. Where if you have millions and millions of data points, whether I have 6 million or 7 million, maybe not make too big of a difference. Right? Then I might as well just pull some out for generalization, testing that way. Okay, so that's all I want. We talked about this before, so I don't want to move on to some other topics. Okay, so the next thing I want to talk about were outliers and how to think about dealing with outliers. Should you? Okay, so the first kind of question on your mind, instead of how to remove them, is the first question should actually be, should I remove them? Okay, so are they actually outliers? And then if I should remove them, how should I go about it? Right? So, I don't think it's like when most people hear about outliers, their first reaction is, okay, I should identify them and take them out of my data set. And my first reaction to that is, that sounds really dangerous, right? It sounds like you're kind of, you can easily, very easily manipulate your analysis by saying, oh, this data point's an outlier. Let me take this out. And that can very easily, because, let's say you're modeling some sort of event like with like with something like nuclear reactors, and you're saying, okay, every 20 years a nuclear reactor melts down, but that doesn't happen so often. So let me take those out of my data set and see what's the average cost of running one of these. Well, it's probably not the right way to do it, right? Even though it's an outlier, right? But I don't want to remove it from the data set just for my analysis. Okay, so I mean, hopefully from that example, you think this is there is a question here of should I remove them, and some of the processes of how to remove them kind of breach dangerously on this threshold of removing too many of them in ways, and so I want to start by kind of walking through some examples which seem reasonable of how to go about finding and removing outliers, and kind of like see if you can figure out ways that these can go wrong. Okay, so I'm not saying you shouldn't necessarily remove outliers, because often they're from these spurious measurements, although they could be these really impactful extreme events, right? But so aside from that issue, you should also kind of take this into account. For instance, let's say I'm predicting kind of the effects of wages on some company, and I want to say what's the average model if I give everyone a 10% raise, how much is this going to affect the revenue of the company? But I didn't, the outliers, the CEO of the company makes lots and lots of money, and so I filtered that out of the outlier, and then I factored that in. That was maybe 10% of the kind of the cost of this event on the company, right? Because I filtered that out. Okay, like it's kind of dangerous just to throw these away. But if I am going to throw them away, okay, then basically let's go back to this thing where I have some model, and I've got some data points here. Okay, and for every data point, typically what you do is you have a model M. Let's say this is the model M. You have example data point here X, right? And now for every data point, I describe its, I map it onto this model. Okay, and this line would be the residual of xi here, right? So this is the residual from the model. So residual, and it basically tells you how well does the model fit your data, right? At least whereas regression, or at least in the regression setting, we have this, usually it was this vertical distance in the one coordinate we were trying to predict. In the subspace approximation, it's this perpendicular thing. In center-based clustering, it's a mapping to one centers. Okay, and if you have a good sense of what is the model, then the outlier should be the ones with the largest residuals, right? So then it kind of hopefully makes sense that the outliers are the data points with the largest residuals, right? So, okay, so what I can do, I can build my model, find the ones with the largest residuals, maybe this one, and this one, and then I can throw those away. Yep.
Is it the residual equivalent to Euclidean distance?
That's the most common way of thinking about it, but it could be anything, right? It could be any sort of, I mean, in all the examples I gave you, say center-based clustering, kind of low-rank approximation, and least squares is Euclidean distance, but it doesn't have to be, right? There's things I've mentioned, these like information theory model distances, and these are used to kind of predict some things based on So if I'm dealing with the point star probability distributions, because they're kind of the average, the probability I use this word within a document because I had a word count vector and I normalized it, then I would probably want to measure it with the native information distance there instead, which would not be Euclidean distance. The model is somehow reflective of that as well. And so there's lots of models in language processing that are built inherently on these non-Euclidean distances, and then that's what you would use here. We didn't discuss those so much, but they're not too different from what we did, but the optimization is set up in a different way. And then if you're doing classification, you probably, it turns out you don't want to use least squares often, you want to use a different loss function, and then that's usually what you want to use as the residual instead. And that scales things slightly differently. Okay, so, but intuitively, Euclidean distance and all the pictures I'm going to draw today. Right, so it's outliers, the ones with the largest residual values. Okay, so what here would be, if I treated it this way, if my algorithm was 1, build model M, 2, calculate the residuals, the set R of X for X and X, and then remove outliers, which are, say, R of X is greater than some sort of threshold. Right? So I had some threshold of distance somehow, and I said the outliers are beyond this threshold. Okay, so if you can imagine, what's the point of doing this, right? You notice in this setup, the first step I had to build the model, and if my goal was to build a good model, then why do I need to remove the outliers? But if maybe I said, well, I didn't trust the model because I have outliers in it. Well, then why do you trust that what you're throwing away are the true outliers? You know, so, you know, there's kind of this chicken and egg problem here. Okay, so one way around this is to say, well, okay, I trust the model enough to throw away faraway points, but I think it'd be better if I rebuilt it after I threw away the outliers, right? Maybe all the outliers were going to be on this side, and I threw them out, and then it moved slightly up a little bit, right? You know, so maybe the solution is after I do this, I'm going to, you know, 4 is go to step 1, right, and build the model over again. Okay? Then it could be that there's still more outliers, and I still remove these outliers. Right? You could eventually keep pruning away points, and there was some very well-known researcher who came here a few years ago and gave a talk about exactly doing this, and I was just scratching my head the whole time, thinking like this seems very dangerous. But he was automating a system for how to do this efficiently. You know, I'm like, if you keep doing this, you might prune away till there's nothing left. You can also say, what is this threshold? How do I set this threshold? One maybe reasonable way to do that, I know I've written a paper at some point that advocated this, say, throw away the 10% furthest away points. Okay, and maybe that's fine once, but if you go back and I keep running this, every way I throw away 10% of the points, and after I do this enough times, I have no points left. You can always throw away 10% of the points. Right, so it's kind of this whole idea of throwing away outliers is a little bit dangerous here. I'm not saying this is entirely bad, but you have to be kind of careful that you're not slowly manipulating the model and it's drifting in a certain way, or that you're just throwing away too many good points and you're losing the richness of what's going on. Okay, you get some comments.
Can you put it straight off standard deviation here, like how many steps you want to, how far actually you want to get? I don't know if it's even within the topic.
Yeah. So you know, maybe I want to set it based on, I think these are basically they're kind of Gaussian noise. So I can actually fit a Gaussian to the residuals and throw the ones that are all the way on the tail.
It has to be a normal distribution, right?
Yeah, so it's a Gaussian one dimension. It's a normal distribution. And if you remember what a Gaussian looks like, right, it's going to have centered at 0, and I can, right, and so it's going to look kind of like this. And so what's going to happen is that within one, how it's defined is you have one standard deviation, 1 sigma. This is going to capture 60, what is it, like 66% of the data, something like that. I don't remember exactly. Then you go out 2 standard deviations, 2 sigma, and this captures something like 95%. You go out 3 standard deviations, and this is going to capture something like 99% of your data. And maybe you say beyond that is probably an outlier. But if you have 100 data points, if you have 1,000 data points, you expect something like 1% of them to fall outside of there. Those are quite perfectly reasonable data points, but you're not seeing them if you're throwing them away, right? So there are going to be data points out here in the tail. And in practice, they should be balanced, but your least squares is going to be kind of the best fit. I'm going to add some bias in some way if I'm clipping off this tail. So these are perfectly reasonable from a normal distribution of noise. Should I throw them away or should I not throw them away? It's hard to know where is this threshold. So it's a good question, but I partially solves it, but I'm not sure entirely solves it.
Still going in circles.
You could, yeah.
Yeah, another just like heuristic that I've heard is, I don't know if you know where this comes from, 1.5 times the interquartile range of the data. Like I feel like I learned that in like basic sense, but I don't know if you've ever heard of that.
Yeah, so I think this there's these box and whisker plots that start, it shows like the 25 to 75 percentile, draws a box, then it draws actual data points outside there. And from a visual point of view, I think this is great for showing them, right? Should you actually throw them away? It's the interquartile range is not exactly, it's kind of not assuming necessarily a Gaussian distribution, but it's going to assume something that's roughly going to be 2 standard deviations somewhere out there. So it's like probably close to what typical p-value 5% or the 2.5% in the tails you're probably throwing away are roughly at there, which would be things that would get rejected from you might throw away from a null hypothesis test, right? Not necessarily that they're bad. 5% of the data should be that far out, but they're outside of the normal things that would happen for most of the data, but not all the data, right? It's kind of like yeah. So yeah. So I mean, this is a fairly reasonable general procedure to use, but just be careful that it's not a magic bullet. Yeah.
So sorry to annoy you here.
No. It's good question.
To kind of get a bigger picture, like when we're doing this, we're clipping up the points that we think are outliers. It basically makes our research and results more biased, right? We can throw out some points which may get in some really crucial data.
Yeah.
Like let's say we do some like medical trials, right? We have some patients that react differently versus like 99% that have this known result, and then if we discard those, we might like actually impose them to danger or something like that we don't.
Yeah, so things like in medical trials where for 95% of the patients are cured of some disease, but 2% of them die with horrible consequences, right? There are rules that you have to mention this. So when you see these, I think when you see these commercials where they list off all these possible side effects, or there are laws that have to, anything that may have happened, it may have been not be related, but they have to announce these sort of things that happen for exactly these reasons. On the other hand, if there's some epidemic that's it's going to spread, and probably everyone will die unless you do this, and 2% of the people die. Then you have these ethical questions, but you could foreseeably say that's still a good outcome. But you'd still want to know about these sort of things, right? How you deal with these gets potentially into some ethical issues here as well. Yeah.
This approach presumes you can't look at it and explain why it's an outlier. Right? If you look at the point and go, that's obviously a missing field, or you could throw them away justifiably. This is dealing with them just statistically.
Yeah, right. So if you know that it's some sort of so if you know it's kind of a data gathering error, yeah. So then you would want to treat that basically as an unknown. And actually, I'm going a little slower than I want, so maybe I should get to how to deal with those. But that's a good point, right? If you know that the data is not correct, then you can obviously do something smart about that. Yeah. Okay. So I want to say one more thing about outliers, and then we'll talk about missing data. Okay. So there's another way of dealing with outliers, which are these. This density-based approach to removing outliers, and that's the idea that if your data there's lots of data points here, and there aren't too many data points out here, that I can kind of build, say, some estimation of the density of the data. I'm assuming that there's some good underlying, say, Euclidean metric underneath here. One thing I can do is say, I can look at a very simplistic approach is to draw for every data point, draw a ball around it and count how many the number of points in some ball of radius r around x. And if this is then say if the size of bar radius r around x is going to be less than some threshold, then I say this is an outlier. Right? So just based on the density of the data, if it's far away from all the other data points, then, or maybe not all of them, maybe there are two things out there, then I might want to throw it away. Yeah?
Is there like a standard way of choosing that radius r?
It's kind of like a magical parameter. Yeah. Maybe if you have labels, you can do cross-validation over it, but otherwise, you're kind of, like a lot of these threshold-based approaches, you kind of pick something that you kind of feel works. There's, usually there's a magical way of doing it that is not explained in the paper or in the code. But someone sets a value and said, I got it by magic, right? So, but there's not some like justifiable mathematical way necessarily. That's true and not true. There are some approaches which I've seen completely justify how to do this. You can make some argument about, okay, there should be some underlying structure where the data is uniform along that structure, and then if that's true, you can detect what that density is by kind of looking at the profile of the density of all the balls and kind of look where the drop-off is and then kind of pick something in this way. I've seen some arguments that do this in some settings. I don't have the terminology to describe them yet, so I'm happy to explain them to you offline, but it's like using competition topology and stuff like that. But there's some cool stuff in those ways. If you're taking, is there a competition topology class? It's this semester, so if you're in there, you can ask Bay about these approaches. But those are super cool, but beyond what I have time to describe. Okay, so this kind of works unless, if you have this magical threshold correctly. You can kind of say, okay, these are outliers, and in clustering, this is maybe kind of the right thing to do. I don't want to assign a cluster to each of these outlier points. Okay, but this doesn't work if I actually have another cluster that looks like this, where I have, what's going on here is I have two kind of main clusters. One is small and dense, and one is about the same number of data points, but they're all more spread out. Okay, so if I draw one of these kind of circles around here, I may not get a lot of points inside this circle, but that's just because that whole cluster is more spread out. The density of data may not be uniform on the points. Okay, and so if this can happen in data sets, I'm going to have, you know, if I look at the employees in a company and their salary, I may have a lot of people who have exactly the same or almost the same salary doing one job, and then people who are working in sales and their salaries depend a lot on how much bonuses they're getting based on the sales that year, and they're much more spread out, right? You know, it could be something like this, that there are these different distributions, and so I can have a dense one and a sparse one, and a single test like this might not be valid. Okay, so a good kind of way of dealing with this is what's called reverse nearest so reverse nearest neighbor, and the idea is to kind of take a data point and find, say, its kth nearest neighbor. Right, so now you could do the first nearest neighbor, but like the 10th nearest neighbor is going to be more robust, right? And then I look at how far this distance is, say the distance from data x prime, you know, the kth distance in some point set. And then I look at, and I compare this, and this gives me some point y. And then I look back at y in the point set, its kth nearest neighbor. Okay, so that, what I would do here is I would look at, color. Okay, so look at this, and I look at its kth nearest neighbor, right, of this point y. It's going to give me a different radius here. And if these two are close to each other, then that probably means that it's near a bunch of other points which are roughly the same density. So it's not necessarily an outlier. And here, these radii would be much smaller, right? They'd both be small because the points are more dense here. So I can filter out outliers in this way. So I now have two parameters. I need to say how different is the distance to the kth nearest neighbor versus looking at that point y and looking at its kth distance. What's the threshold of how different do these have to be? And usually look at a ratio of them instead of an absolute difference. And how do I choose k? Right, so now I have these two parameters, but this is more robust than just looking at one radius here. So I have two magical parameters, but they're both less sensitive on the data. Okay, so this is a bit more effective way of pruning based on outliers, based on the density here.
Is it the same as k-means algorithm when you do clustering?
Yeah, I mean, you could use this within k-means to say, I don't want to assign a cluster to a bunch of points that are pretty far off. And you could set k as like, well, if there are, you know, if I say there are 100 points that are worth, if 100 points are worth putting a cluster around, so then if I'd set k on the order of 100, right? So maybe I set it at 30 or something like that. I don't need the full distribution, but something like on the order of 100, they're worth keeping. Well, then for a bunch of them, with the distance to the 30th nearest neighbor should be approximately kind of, it should be uniform. Right? Something like mixture of Gaussians will actually handle this somewhat naturally. It's whether it can fit a reasonable Gaussian to a number of points, and it can adjust the bandwidth dynamically in that way. But otherwise, you can filter them out this way. This is more robust than just density. Okay, so I have 15 minutes left. I want to talk about missing data. Okay, and so this actually comes up a lot, and we're going to talk about it in the context of I have a data set P, and I'm going to think of this as an n by d so matrix. And I'm going to define a set set omega, which is going to be a subset of I and j in n cross d, right? So these are the elements such that Pij is not equal to the empty set. So I actually have a reading, okay? So this idea that I have some matrix P, but I only have readings in some of these cells. And most of it might be, I just don't have any readings there. So, for instance, say that I have an example here would be that each row is going to be a movie, right? And then each column is going to be a user who's rated the movies. So most movies, not everyone has seen, right? And so I don't have ratings from everyone, and most users have not seen every movie, right? It could be different density, different movies, and different ratings, but this is not complete. And so, how do I make predictions on this when most of the data is missing? It could also be I just have one or two things I know were written down wrong, and I filtered those out. Now I need to try and replace what those are. Okay, but typically what I'd like to do is make personalized recommendations onto these users. Okay, so I'm going to define, so just for some notation, I'll say that I'll have some projection operator. This will give me the elements. This would be width, scores, and I'll say the perpendicular part will give me the elements without scores. Okay, and so so I want to try and fill these in, and there's kind of a simple way that initially you'd come up with is I'm just going to fill in everything with the average of the row or the average of the column or the average of the row average and the column average, something like that. This is okay. It kind of knows, okay, if I give you just a random user, what do I predict the rating is going to be? And that works okay, but it's not personalized onto the user. If a user likes horror movies but not rom-coms, then they're going to have a different predicted rating than someone who has the opposite effect. Okay, who has the opposite kind of likes. If they like rom-coms but not horror movies, then they're going to react very differently than this average person. So I want to somehow personalize these ratings onto people. And so Netflix, kind of, you've heard this Netflix challenge. We'll talk more about it on Wednesday, actually. But this was a big instance of this problem. And there's a lot of cool research that came out of this context. Okay, so they want to make predictions, personalized predictions for all of these users. And so the idea is that there's this latent space of what users really care about, and that means that the matrix should probably have low rank. Okay, so I'm going to set up an optimization problem that's going to be described as, I want to find this P star, this filled in, this complete matrix, which is going to be an arg min over all possible matrices X. That's going to look something like the projection Okay, so I want to minimize the Frobenius norm on the parts of the matrix where I have readings on X. But I also want to enforce something that X should be low rank. Okay, and so what's typically done is what's called, you add a regularization term here, and this notation is used to describe what's called the nuclear norm. Okay, and this is equal to the sum of the singular values. Okay, so remember the squared for B sum is the sum of the squared singular values. This is just the sum of the singular values. And it turns out this is the kind of the right way to regularize to try and make sure that the matrix you come out with is biased towards being smaller rank. Okay, and so this the regularization term tells me how the larger I put that, the smaller the rank I would like the matrix to be. Okay, and so that use maybe cross-validation to figure out what the right term for this would be. Okay. All right, and so this is basically kind of the common. There are other ways to formulate, but this has kind of been the generally accepted upon good right formulation for this problem. And if you can solve for x, then it will give you a low rank matrix, which will try and match pretty well on the observed values and fill in everything else. And kind of this is kind of the basis of what's used for like the Netflix recommendation system problem, or in when Amazon recommends other products for you. This is kind of the basic kind of version of this. There are other bells and whistles they put on, but this is inherently what they're trying to do. Okay, and it may not be an actual recommendation rating. On Netflix, they've moved away to that to see how long did you actually watch it, right? If you like it, you presumably watch more of a show. On Amazon, maybe it's not just the star rating, but if you bought it, then that's a win for them. They don't necessarily care if you like it or not. They probably want you to like it to come back for more, but the important thing is that you actually give them money, right? So how do we solve this, right? There's not kind of as clean of a closed form anymore, but there's a nice iterative algorithm that's not too hard. And then when it gets big, there are some issues, but basically the basic format goes like this. So matrix completion. And you're given a set and some lambda parameter. So how many of you have had a class where we've learned matrix completion here before? Okay, good. So first year I'm teaching this, so I'm glad I did this. Okay, so start by initialize x, right? And it could be something like this simple way of doing this is each xij is given kind of like the average of row and column, of P of the, this is what I would give x, I would say, or this, right? So if I actually have data there, then I'll put this in x. If not, I'll just initialize as something simple. Okay? The average of the columns, where I give everything a rating of 3 out of 5. Okay? Now I want to repeat. I want to do so I'm going to repeat something until I converge, and there are only 3 steps I have to do. So I'm going to do USV transpose is going to be the SVD of x. Okay, so I'm going to use my favorite SVD operation again. 2, I'm going to do some trimming operation onto x. So I'm going to I'll call this operation phi of lambda of S V transpose. And I'll explain what this operation is. So I'm going to kind of trim the singular values in some way using lambda, it's going to be kind of like the frequent direction step. So I'm going to, this will be make it closer to low rank, but it'll adhere to this cost function here. And then I'm going to update x is going to be, so if I have a reading, if I actually have a data point, I'll keep that data point. But if I don't, then I will use what I have in X star. Okay, so the missing parts I'm going to use from X star, but I'll put back the parts from the actual data I have, right? So because I put these back, it's not going to be exactly so low rank again. These are going to be not exactly fit, so I'll do this until I'll say it so converges. And so what converges means is you can make a choice, but maybe that between two rounds, the x I get, the Frobenius norms, the difference between them is close enough. Something like that. Until it's not changing too much in between rounds. Okay, so now I need to explain this operation. And so this phi of s is going to be, so I'll say this is going to be S1 minus lambda plus S22 minus lambda SDD minus lambda. Okay, so it's going to stay a diagonal matrix where this operation x minus phi plus is going to be equals to the max of 0 of x minus lambda. Right? So I'm going to shrink the singular values by lambda, but if it drops below 0, I'm going to cap it at 0. So I don't shrink anything below 0. So if I basically, all the singular values that are below lambda, I snap to 0, and everything else I just shrink by a small amount. Okay, so what this is going to do is anything that, for some parameter lambda, if it's below that value, I'm going to remove the rank. I'm going to reduce the rank of this. So the larger I set lambda, the more I reduce the rank, right? Which is what I said here. The larger lambda, the more I enforce this nuclear norm constraint, the smaller the rank will end up being, because I am biasing towards a smaller rank thing. Okay, so that's what's happening here. This step forces it, kind of regresses it, biases it towards being a smaller rank, and then I add these values where I actually know the values back in, and I repeat. Yeah?
What's a good way to choose lambda?
Magic again, yeah. So what you should use cross-validation. You can do cross-validation. This is the right thing. You can hold out some of the data that you have and run this algorithm with different lambda and see which one do better on the held out data, is what you should do. That's yeah, so I do have a good answer in this case. You can use cross-validation. Yeah. Yeah, so this is the matrix completion problem. You know, it's a simple use of the SVD. And this works much better typically in a lot of cases than taking the average of the rows and columns. It will adapt it so that, you know, it will specify to the user. So basically think there's a low dimensional space. Each user kind of fits in that space someplace, and that tells them, do they like horror movies or rom-coms or thrillers or kind of sci-fi, and it gives them some kind of profile. It doesn't explicitly do that, but implicitly does, and it gives them a rating based on that, right? And each movie probably also has like some meaning within each of those domains, and kind of how much do you weight them. It's kind of implicitly doing something like this, and it's saying that that model can't be too complex based on enforcing it to be lower rank. You know, you could do something else here. I could instead just say, I want rank K, So take the top k eigenvectors, or top k eigenvalues, zero out everything else. That would probably work as well. This is a little bit more stable, that if the k and the k plus 1 thing are almost the same value, I would probably either keep both of them or throw both of them away. So it's going to be, and that way it's a little bit better way of doing it than just setting a k value, because this turns out the lambda is a little less finicky to boundary cases than a hard choice of k, is kind of a rationale for doing it this way. Also, it fits this problem. It fits this exact formulation, and a lot of people in research like to say, I want to write down a specific objective and then solve it. And so they can do it this way, and then you can regularize over that. All right, oh, and then let me, one more thing, return x hat. So I don't want to return x, I actually want to return the low rank solution probably here. So before doing this last assignment. Yeah. So this was kind of a tour of thinking about noise. We're going to talk about privacy and some issues which are kind of related to noise as well. On Wednesday should be another more kind of fun lecture covering lots of different things in the history of privacy in data. And your dimensional reduction homework is due on Wednesday. And if you want to, you can go to this thing for the club in 10 minutes on deep learning. So.